Hi, hello everyone. My name is Luz, and like Divya said, I used to work in developer relations in Opera Software, doing some evangelizing web standards mainly. And this is what I'm going to talk about today, one of those standards, device orientation, or as sometimes I thought it should be called when working with it, device disorientation, because you will see now it looks pretty weird, but it is also pretty powerful and interesting. So when I talk about device orientation to a lot of people, I sometimes, or a considerable amount of times, I get, oh yeah, portrait and landscape thing. And yeah, well, if you're wondering if that's what I'm going to talk about, no, that's not what I mean. I mean the other orientation thing, the angle thing. So I'm going to start talking today first about what device orientation is. And I'm going to talk about the API and what it can be used for. I'm also going to show a demo I made. Then I'm going to talk about some mathematics you need to know to use the device orientation API, because unlike other web APIs that you may be familiar with, device orientation requires a bit more of mathematics than the usual. Then I will show some code. And finally, I'll talk about browser support and the different implementations, and some tips and tricks that you might be interested in if you're going to use device orientation in your web applications. So first, I want to ask you, how many people here have used device orientation in the past? Okay, some people have, most people haven't. So let's have a look at what device orientation is. So device orientation is an API that allows you to know basically three things about your phone. So, hello, can you hear me with this one? Okay, so I'm going to show it with a tablet. So you can imagine that this is just a big phone, or a tablet works too, but we will see later why that's more complicated. But let's imagine this is just a big phone. So what device orientation tells you is at what angles you're holding the phone, so the different orientations in which the user is holding the phone. It also tells you the speed at which the user is tilting the phone, and finally the acceleration that the phone or any mobile device is being subjected to in each of the three axes that you're seeing on the screen. So it has, how does it do it? So how do you get the information from, how do you get it? So device orientation has three different events. The first one is called device orientation, which is the most famous, that gives you the angles. This is what we are going to see in the demo. Then device motion, which gives you the angular speed or the rate of change of the movement, and it also gives you the acceleration and some other things that we're going to see later. And finally, compass needs calibration, which is exactly what the event says it is. It's an event that's triggered when somehow your browser thinks that the compass that is built inside the hardware needs to be calibrated. And then what usually happens is that the browser itself shows some UI to the user and asks the user to perform some movements in order to calibrate the compass. So you shouldn't be too concerned with the last one. We're going to see the other two. So what is it good for? I would say mainly two different kinds of things. So the first one you can see there on the left is, for example, is what I call a static application, which means that you measure the angles and then you make a one-off use of that. For example, when you have to decide on which orientation you're going to show a map to the user, and you want the user to see the north of the map pointing to the real north. And the other thing is dynamic or interactive use, in which you want the user to move the phone around, and you want to be able to capture this movement and do something with it. What I'm going to talk about today is the second one, the dynamic and interactive, which is obviously more complicated, but also more interesting in the sense that if you manage to master that one, you can obviously also use it for the simplest or one-off static purposes. So let's start with the first part, which is device orientation and the angles in which the user is holding or positioning the phone. What I'm going to start showing is I have a demo, and that demo is that's a WebGL model of a teapot made in Three.js. And what I'm going to do is I'm going to use my phone. My phone is connected to my laptop using WebSockets, and I'm going to move my phone around, and I'm going to move I'm going to use it to move that teapot around. So, okay, just sorry about that. Okay. All the speakers connected to the Wi-Fi, please. Okay. It is supposed to be much smoother than this. Let me try and see if, okay. So, you can see it turning, but it's not really, not nearly as smooth enough as what I would like it to see. I have a video backup for it. Just let me try one more time. Okay. No, it's really not working. Okay. So let's have a look at my at the video backup. So there, I don't know if you can see that. That's the same thing on the my laptop, and there you can see how it really works and how the phone is making it tilt. So it's the same movement in the phone being translated to the model. Okay. So now that you have an idea, more or less, about what it is, let's have a look at what and how it is done. So the first thing, like any 3D application or any application that has to do with any three-dimensional movement, mostly I would say the core of it is the mathematics of it, and that's usually the hardest part and difficult part. So I'm going to go through some pretty unusual mathematics for a web development or web technologies conference. So please bear with me. Even if you feel that I'm walking you through this, just bear with me for a second, and when I get to the code, you will see that it's a lot simpler than it looks when you look at formulas and matrices. So if you have ever taken a plane, you're probably already pretty familiar with the mathematics of three-dimensional movement. That is because the same convention or the same system of reference that's used for the navigation or the movement of an airplane is the same one that's used on the spec for device orientation. So how does it work? This is called Tate-Bryan angles, and the way it works is that you have basically three axes that you're concerned with. So the first one is where the plane is heading, the airplane is heading in the plane of the Earth. So by this I mean, is it going north, east, northeast, northwest? So that's basically this direction. And it's turning around in an axis that's always pointing up. The second one is the pitch of the plane, or how much it is climbing or descending. That's how much it is pointing upwards of any direction that it's going to, right? So if it's climbing 45 degrees and going north, it is still 45 degrees. And if it's climbing 45 degrees and going south, it is still 45 degrees. So that's what in the spec is called beta, and that's the pitch. And third, you have the bank or roll, which is how much the airplane is tilting to the sides. So this sort of thing, which in the spec is called gamma. And again, the tilt is, the bank is the same bank independently of if I'm going north, south, climbing, or descending, right? So that's an important fact to remember, because that's a key thing for the mathematics that we're going to be doing later. So this is how it looks in the spec. You have the Z, which is always a vertical axis, and alpha, which is the heading in the plane and the alpha movement on the phone. Then in that image over there, you have beta, which is the angle that you turn around an axis that's always pointing to the side of the phone, so this one. And then you have gamma, which is always pointing towards the top of the phone, and is this movement, or the banking of the plane. So these diagrams seem a little bit deceptive, because in each of them, the phone is only moving, or the angle, only one angular movement is being represented. When in reality, what happens is that you have the user tilting the phone in multiple dimensions. So what you have is something more like this, in which, just one moment, I think I'm gonna have to, let me see, okay, there you go. I want to stop it for a while. So what you have actually is something like this, in which first the axis, the blue axis, is an axis that's fixed to the world. And the red one is an axis, is a system of reference that's fixed to the phone. But as soon as I turn in Z, you can see that my X and my Y are moving. And when I will turn in X to turn in beta, I will be turning with respect to the new X, which is the red thing pointing slightly downwards, as you can see in the next movement, right? So each of these movements, or each of these movements the user does with the phone, occur with respect to the system, a system of reference that has already been rotated with respect to a previous axis. So that's where, that's the key thing in order to know how we are going to finally apply the rotations, and how we should apply the rotations. So this is the scary slide. Please don't all of you walk out. Just don't mind whatever it is that is inside those matrices. I will explain, and it's easier than it looks, really. So if you want to apply a rotation, the way you do it is you have your vector that is indicating your current angular position, and you have to multiply that by several rotation matrices, or you have to apply rotations in terms of the axis around which you're going to rotate and the angle that you want to rotate that, the amount that you want to rotate that, which is the angle. So what you have there, that V0 thing on the right, that's a vector, and the way that we apply rotations, or we have to multiply matrices, is from the left. So the closer matrices are going to be multiplied first. So that's going to be the first one right on the left, and then the other one, and finally the one on the far right. And the way it works is, because alpha is the absolute one and Z is always pointing up, you're going to apply that one first. So there you have in the first line V0 being multiplied, but being rotated an amount alpha around an axis Z. Then after that, we apply beta, and we are going to rotate that not around the absolute x, but around x prime, which is the rotated x that appeared after we made our z rotation. And then we're going to rotate around y second, which is the y-axis that came up after rotating first in z and then in x. So just forget about everything that is inside there. Those are matrices that you can Google for. Those are typical formulas that you will find for the rotation matrix, for the z-axis, and angle alpha, and so on and so forth. And you will see that different libraries have a lot of stuff to make your life easier, so no need to freak out about that. But what's also important about the Tate-Bryan angles and that system of reference is that there's something that you have to be careful about and something that can happen, because I mentioned that the angles around which you're rotating shift around, right, with each rotation. So you have to be careful about something called an alpha-gamma singularity, which happens when your z-axis is aligned with your y-axis. And how does this happen? This happens because z is always pointing up, and y is always pointing in the direction of the top of your device, right? So if you point the top of your device up, then you have z pointing up, and you have y second also pointing up. And then when you turn your, the user turns their phone like this, you no longer know if you're rotating in alpha or you're rotating in gamma. And this is, there's also a further problem with this, which is that current hardware that we have on the phones does not really allow you to track any rotations like this for different reasons, because the compass that allows you to do this doesn't work, and the accelerometer that allows you to do this doesn't work in the vertical direction. So you're pretty much at a loss there, and you can find several discontinuities in your gamma and alpha angles. So you have to take that into account. I'm not going to go farther there, but that's something that you want to know if you're going to use it. So now, I hope you're not really too disoriented, because now I'm going to show the code, and you will see that all languages that deal with 3D, as well as most libraries, that, like 3JS that I used for this example, already have a lot of functions built in, and you don't have to deal with any of the matrices that we saw in there. So let's go for the code. So in my application, it's a very simple application that just gets the angles in the phone, on the phone, then sends them using WebSockets to a server, and then they're broadcasted to the model that uses, and then 3JS is used to move the model around. So let's look at the remote JS code. So there's a lot of WebSockets boilerplate there. Just forget about it and look at the third line. It's just the simple matter of adding an event listener for the device orientation event. And then once you get the event, you can see there that I'm using the alpha, beta, and gamma and sending them to the server, right? So this looks really simple. And then on the other end, I have the model code, and the line that matters is the line that has the big red arrow next to it. And you can see there that I'm simply using this 3JS method that says I simply have the teapot, which is my model, and I'm applying a rotation directly, because as you can imagine, this Tate-Bryan system of reference and this kind of rotation is not only a device orientation thing, right? It's like all around like any 3D application. So obviously most things have built-in functions. So the only thing I have to do is I have to decide which angle I want on the X, Y, and Z axis, which are the different three inputs that this method has. And the only thing I'm doing is the 3 lines before the line with the red arrow, I'm converting the angles from degrees to radians, which is what 3JS uses, and then I'm using them directly. And if you pay attention carefully, you will see that alpha and beta are switched, And that's because in WebGL, Z is Y and Y is Z. But that's just a detail in case you want to use device orientation with WebGL. So as you can see, it's a lot easier than the math would imply. And if at this moment you're wondering why I explained all the math, it wasn't just because I wanted to confuse you. It was actually because I guess that if you want to do a very simple thing that I just did, you can always get by with the built-in functions. But it's always interesting to know how things really work. Especially I will show later, or I will actually just mention later something that's really useful and really nice to have that makes use of all this math and where all this math really comes in handy. But let's talk now about support and the different browsers and how they have implemented device orientation. So what I have kind of used here, and I'm sure you're all by now familiar with it, and if device orientation is a mobile feature, right? So if you look at the right-hand side of that screenshot, you can see that for all the mobile browsers, it is green, right? Except for Opera Mini. So there's like pretty good support for device orientation. Still, there's a sad panda in my slide. And the reason for that is that when I started trying to use device orientation in real life, all that green didn't exactly reflect my experience with it. So what I did is I made a couple of tests that you can find at luzc.github.com/webtests and orientation, compass, and motion for each of the different events. And I ran those tests in a couple of browsers. I ran those in Chrome, Firefox, Opera Mobile, and Safari, and then I went and looked at the spec. The spec is the bottom line, the bottom row. And what I found was that although this was supported everywhere except in, no Windows 8, but everywhere else, the fact was that look at the first column, look at the bottom row, that's what the spec says. It says that 0 should be pointing north, and that you should have your angle increasing counterclockwise. And then if you look from their app and you look at Safari, you can see that Safari does what the spec says it should be doing. You look at Opera Mobile and it also does what the spec says it should be doing. But then you look at Firefox for Android and it has a 0 in the right place, but it increases in a clockwise fashion. And then if you look at Chrome for Android, you can see that it increases counterclockwise as it should do, but then the 0 is pointing west instead of north. And then if you take more time to look at the rest, I'm not going to go over the rest of the table, but you will find a pretty similar situation. So although it is supported, it is not as easy as it seems to be. And another thing I also found out is that portrait versus landscape matters. So I don't know how much you can see the content of those screens in there in my picture, but these are both Opera. But if you look at the top one, it says that alpha is 85 degrees. And if you look at the bottom one, you can see that alpha is actually 1. So why is this? Because actually Opera thinks that my phone is a portrait device, so it's pointing that way. But my tablet is a landscape device, so it's pointing that other way. So that's why there's approximately 90 degree angle difference in the measuring of alpha in there. And finally, it wasn't just about portrait and landscape, but there were also different browsers that had different ideas about how you have to hold your landscape device the right way. If you look at the picture on the left, you can see how Firefox thinks that you should hold your landscape device. And if you look closely, you will see that the cable is right there on the left. But if you look at the other picture, and you look at how Opera and Chrome think that you should hold your landscape device, the cable is on the other side. So, what do you do with all this, right? So the answer to this is there's no easy answer. You have to bring your own calibration to the table, and you have different choices to do this. So how can you do it? So the first option is, if your application allows it, you can just use the relative, the relative angle difference to whatever position the user is holding the device when they launch your application, and then you just see how much it moved or how much it deviated with whatever you consider, with respect to whatever you consider to be the standard position. So in that way, you create your own system of reference for each user that's using your application. The other way would be to play dirty and just try to figure out which browser your user is on, and then try to adapt that table that I made inside your application. Although this may backfire, because if ever the browsers change in order to adapt to the spec, your application will go all crazy on you. And the last one that I would recommend, but obviously involves more work, is that you create your own UI for calibration, which consists on making your own little test for your user and asking the user to perform a small action that will allow you to figure out which system of reference they are using. This could be, for example, I don't know, aligning something or turning the phone around in whatever way you think is good for it. And now that I'm giving out tips, there's another thing, and this is what I mentioned earlier, where the math comes in handy. And this is you. Well, I didn't manage to show it live. The example I will try later when I'm done with the talk. But something that happens is that because the sampling frequency is so high, sometimes you will see that things are very shaky, that are very responsive to any small movement. So you may also want some buffering in your application, and this is where the math becomes really relevant. And I'm not going to go into detail right now because it's a little bit complex for the time we have, but if anyone is interested, I will be more than happy to talk to them about this later. Rich Tibet from Opera has a really nice demo, which is a compass that uses this buffering technique in order to get a smoother movement. But now I would like to briefly go into and mention the other part of the device orientation API, which is device motion, the other event you have. And like I said, this allows you to get the rotation rate, the acceleration, another version of the acceleration, which is simply that, the acceleration with gravity, which is the same acceleration that you see in point 2 with a force equal and opposed to gravity added up. This is just a matter of hardware, because some hardware is not capable of detecting the acceleration without the effects of gravity, but they're basically the same thing. And finally, interval is the interval in milliseconds at which these angles or these different magnitudes are being sampled from the hardware. So what I did again was I ran my tests, my motion test, in my Samsung Galaxy Tab and iOS. But what I found, unlike the other case, is that there's no uniform support for any of this. So you can see there that Safari gave me the acceleration, Safari, Opera, and Firefox gave me the acceleration, including gravity. Safari gave the rotation rate, but just Safari alone. And then I could get the interval for Opera, Safari, and Firefox, but Opera and Firefox produced an interface in milliseconds, the way the spec thinks it should be. But Safari just had I don't know, a strange measure. I mean, it had an interval, but I couldn't really say in what units it was measuring. So yeah, and I couldn't get it it didn't work in Chrome for me. So if you're still curious about how this is used, it's pretty much like the device orientation event that we saw earlier. So you just add an event listener to device motion, and then you get the acceleration in X, Y, and Z, the acceleration with gravity in X, Y, and Z, and then you get the rotation rate in alpha, beta, and gamma, and finally the interval. So no secrets here. So I would say this is pretty much it. I know it's a lot of it, and it's just very high-level overview. But if you have to remember anything about it, I would say the important things are The device orientation gives you the angular position, angular speed, and acceleration of the phone. It works on the, it gives you all this information with respect to the intrinsic axis of rotation. That means that rotations have to be applied in order, so the order matters. You can find the singularity in alpha and gamma, and you have to watch out for that. But 3D libraries or languages involved in any type of 3D development can make your life a lot easier, like we saw in my code. Browser support is good, at least for the device orientation event, but implementations are very different, and you need your own calibration for it. Portrait and landscape matters, and you may want some buffering. And finally, device motion has only partial support. So I will try briefly to see if I can show my demo and my demo works before I open the talk up for questions. It seems to be doing better. So you can see that it turns around this way. And you can see how it tilts in this direction. And then finally in beta, right? And what you can see on the right, I don't know if you can see that. Those are the angles changing. So yeah, well, I'm not, I don't have the best files, so you can see them changing all at once. But I think this is a pretty good illustration of how it works and what you can do with it. So yeah, and I think that's it. And that's that's all I have to say. And thank you. Yeah, just if you want to see the demos or ask me any questions, the demos are on github.com/LuzC, and that's my Twitter handle. And thank you all for listening. Yeah.
I understand how you can get device rotation. We were working on an application, though. We were trying to figure out if we could not only get device rotation, but also location in 3D space. Do you know if there's any tips or tricks that we could use to try to calculate that?
Yeah, actually, there's no spec that I know that gives you that, but I know there are a lot of tricks from my time doing user experience. So there's a lot of, it's a little bit outside the scope of this, but we can talk about it later. There are a lot of methods that, for example, use the camera, and then when you go, when the person moves the phone, the camera is filming the background, and then they do some filtering of vertical and horizontal elements in the background, in the landscape around, and then they use this to track the movement in the different axes around. And then when you have this vertical and horizontal movement in one direction and you couple that together with the angle, you can pretty much say where the phone is. But this is, I don't know, just all experimental, and if you want, we can chat later and I can refer you to some papers that I've seen that do this.
That'd be great, thanks.
You're welcome. Any other questions? Okay, that seems to be it. Thank you.